All right, ladies and gentlemen, we will begin with Unit 5, Aqueous Chemistry, Chapter 4 in our book. This unit has us looking at double replacement reactions, single replacement reactions, and solution-based stoichiometry that we will cover. But first, we must talk about some other terminology things so that we're all in the same boat. Just so that we all know that there are a few terms that we need to make sure that we highlight. First is that a solution is a homogeneous mixture, and that a solution has two parts, a solvent and a solute. The solvent is the thing that is going to be doing the dissolving, or where the solute is dissolved inside or dissociated inside. Now, a solution is really anything that is aqueous that can be deemed as a homogeneous mixture. As discussed many of times earlier on there in the periodic table and chemical reactions, other units, many things that we see in our regular lives as a liquid actually is known as a solution, but not an answer, in that there's something dissolved or dispersed within water, and because water is one of the most common solvents that we have, and that's where we have that misconception that we have that all solutions are liquid. There can be technically some that are gases, so we have to be careful about that. But solutions are not liquids, they are aqueous. And we will really hammer on that when we look at what do we mean by aqueous. That is that AQ that we had been using for aqueous, meaning it's kind of water-based for that. Again, it has two parts: the solvent, the material that's going to be doing all of the dissolving, or where everything is inside or kind of meanders through, and then the solute, and that's the part that is dissolved or dispersed within the solvent. And we need to make sure that we understand which one is which, because sometimes it can be kind of a little confusing. I mentioned this term earlier, and that was that we also will have the term dissociates, and that is something that is being kind of in a polar solution, will dissociate those ionic compounds, or polar compounds as well, and they will dissociate. So the side that has that negative charge will be attracted to the side that has the positive charge, and vice versa. And so we can see in this picture here that the water molecule, which is polar, is going to be separating the parts of sodium chloride, which is a type of ionic compound, very most commonly known as an ionic compound, for salt, even though all salts are considered any ionic compound. The sides of the water molecule that are attracted to the green, or the chlorine atoms, are those that have that positive end, and then the ones that are attracted, the side of the water molecule that is attracted to the purple circles, is that which are the sodium molecules, is the negative side of the water molecule that we can see. And that this whole process is dissociation. It is not dissolving, they are dissociating, because if you get rid of the water, the salt comes back. Now, it might not look exactly the way it was when it was placed into the water, but structurally speaking, it will be very similar. And so when we look at these types of things, there's some terms that we have probably used in our everyday lives, and that is, what is an electrolyte, and that is something that has an ionic compound that is dissolved or dissociated in water. And so a non-electrolyte is something that may dissolve, but it does not dissociate in water. A lot of times our electrolytes, when we talk about, say, like a Gatorade or a Powerade or one of those other sports drinks, is that they're trying to replenish your electrolytes. And well, a lot of those types of sports drinks have a lot of sugar in them, which actually dehydrates you. Even further, these electrolytes that they're saying that they're trying to replace are those of usually a salt, and so a sodium, magnesium, calcium. Those are the cations that they're trying to replace, and that we actually need for our cells to function properly, if we remember back into our biology classes. When we know we have a strong electrolyte, if we were able to utilize a light bulb, and that a strong electrolyte will allow the electricity to pass, as we can see in the sodium chloride solution. Whereas a weak electrolyte, sugar is not an electrolyte, and therefore does not allow that electric current to pass through the solution. And actually, pure water with no, even distilled water, might have some impurities in it, so that might still conduct a little bit of electricity or allow electricity to pass through it. But that's not what they're looking at. Is pure water, deionized water, so there is nothing but just the H and 2 and the O present in that. And so we can see how that works. Now, the stronger the solution, it doesn't mean that it's going to become lit, and which is popular, I guess, in determining of those words. But we do have that, is that it does just, the light bulb becomes lit, and therefore we see that happens. And so that's what we're looking for. Now, when we talk about double replacement reactions, there is the formation of precipitations, and because in these types of reactions, we're looking for things that form a solid. And because we're going to have two solutions forming a solid, and therefore that is going to be our key indicator that a chemical reaction does occur. I have 5 rules of solubility. There are other references, books, or teachers can have more. These are just the ones that I like to do. Some of them combine, but it is important that we know not just the rules, but the order in which they are given. First off, all elements in group 1 and ammonia salts are soluble. So I like to remember it as group 1, rule 1, group 1. And ammonium is the only cation that is, only polyatomic ion that is a cation, and therefore it's also kind of in there. Some reference materials would have ammonia as its own rule, and it would be rule number 2 usually. I don't like that. I think we can combine them all because they all have a positive 1 charge, and we'll work with that. And so if we see a compound on the product side, and this is really where we're looking to try hopefully identify, is something that's on the product side, is if it starts with a group 1 or ammonium, it is going to be soluble, meaning it's going to be aqueous. It is not going to form that precipitate. Rule 2 is acetates and nitrates, and that they kind of rhyme, so I kind of like having them together, and they also form all soluble salts as well. With that, you'll find that you'll need to make sure that, again, Rule 1 is being followed, then Rule 2 is being followed in that specific order. When you see a compound that has a group 1 or ammonia salt and also has an acetate or a nitrate in it, it's not soluble because of the acetate and nitrate. It helps, but it's not the reason why. It's because of the Rule 1. Rule 3 halides, the halides group says that also they are all soluble with the exception of silver, mercury, and lead. Now, the example I have here shows an example of mercury 1, but I believe even mercury 2 also has are not soluble. I usually look at it as the exceptions to the rules of solubility come to things that you wouldn't really want to ingest, such as you wouldn't want really probably suggest eating silver, mercury, or lead, especially mercury and lead, as we know that these do cause neurological diseases. So anything in group 7. So rule 3 has 3 is kind of the way I remember it, and that it has 3 exceptions. It is going to be the exceptions that make our understanding and remembering of the rules difficult, because it is the exceptions that do have that difficulty in it, that where these are. By cutting down the number of rules, we cut down the number of exceptions, we cut down the number of ways in which we can make mistakes. So rule 3 has 3, and no other one has exceptions to that. Rule 4 also has exceptions, and that is Rule 4 is SO4. So Rule 4 deals with sulfates. And so they are also all soluble, with the exception of our heavy group 2s, but also lead. And I didn't include it in here, but mercury would have been included just as well. Sometimes we find that mercury is usually very difficult to get into solution. There are going to be some things that with this that we're not going to discuss, because again, this is a high school chemistry class. Some of the things that we deal with, such as slightly soluble salts, that's just kind of really adding a lot of insult to injury, is trying to figuring out those slightly soluble. When we get into the lab and we actually see some of these things working, we might notice like, hey, why does this form a precipitate when it's supposed to be solid, soluble, and therefore you start to see some of these exceptions, or you start to see some precipitate but not a lot of a precipitate formed. That's going to be because you have this idea of slightly solubles, and sulfates really get into the slightly soluble stuff. A lot of it will depend on conditions, and we don't need to bother ourselves with that. So again, Rule 4, SO4, those salts are soluble with the exception of our heavy group 2s, lead, and probably also mercury in that as well. And Rule 5 is anything we haven't talked about yet, it's all insoluble. There are the exceptions of the calcium, strontium, and barium sulfides, calcium, strontium, and barium hydroxides. Now, one thing about the hydroxides in group 2, they are not actually all that easy to get into solution. Again, it's all about conditions. We'll talk more about how do we get things into solution that are difficult to get into solution. We'll worry about that later, but they are technically soluble. It just takes some work. And so that's where we get into some of those. And so we have to be careful about it. So again, make sure you know these rules. Make sure that you know these rules in the order in which they are written. As we'll see, if you go beyond some of these rules, you'll start to contradict your own rules, and that's not what you want. You want to have a nice, it's this, and then you don't move on. So when we look at this first one here, we see that predict whether the following are soluble or not. So if we look at the compound sodium carbonate, it's soluble because of rule 1, and that's it. And then we don't move on. We don't move on to rule number 2 because it doesn't deal with it. And if we did, we would move on to all the way to rule number 5, and we'd say, oh, it's supposed to be insoluble because of the carbonate. But no, it's soluble because of rule 1. Once you have a rule that says it's soluble, you don't move on to try and find something that contradicts it. So again, we look at that rules in the order in which they're written. Part B, tin to acetate. Well, tin is not a group 1 element. It's not an ammonium salt, so therefore it must be soluble because of the fact that it has acetate. So all acetates are soluble. So it's soluble. We don't move on, we don't look at anything else, and none of the other rules actually even apply to this one as we see it. Letter C, we see silver chloride. Well, silver's not a group 1 or ammonium salt, so rule 1 is in effect here. However, we have, oh, wait a second, chloride is not a acetate or a nitrate, so that doesn't matter. But it is, rule says that it is soluble. All solubles, all group 7 or 17 or halides are considered to be soluble, except for the fact that silver is an exception to the rule, meaning that this compound is insoluble. It is actually extremely insoluble, and silver will find chlorine atoms almost instantaneously when it's there. It's you can just put, if you're wondering if you have silver in your solution, you just put a little bit of chlorine, salt water in there, and it will precipitate out right away. Or you put silver nitrate into a solution that you think maybe might have chlorine in it, and it will precipitate out right away. And that's why it's actually really hard for most high schools to get these tests done, or even to get silver nitrate to dissolve or dissociate into water, because a lot of our water has chlorine in it for purposes of contamination and decontamination. I'm making sure that our water supply is not growing things in it. So it is important that it's there, but that's what makes it very difficult. Part D, it says barium sulfate. Well, barium is not a group 1. SO4, I always said rule for SO4. Well, that means rules 2 and 3 don't apply here. So when we look at it and say, oh, okay, that SO4 says that all salts are soluble, with the exception of, again, it's the exceptions that get to be really sneaky, in that strontium, barium, and lead would be insoluble, and barium sulfate is considered to be insoluble. And so we will have that come out of solution and form a precipitate if it comes in, that barium comes in contact with the sulfate ion. And the last example is the iron 3 carbonate. And so iron is not a group 1 or an ammonium salt, and so we don't rule there. Rules 2, 3, and 4 don't apply because it's not a nitrate or acetate. It might look very similar, but it's not. You also have the fact that it's not a halide because you have a polyatomic ion present. It's not SO4, and therefore we would say, oh, look, therefore it must be insoluble because Rule 5 says it's insoluble. And that's what we look at. I think right now would be a good opportunity for us to go into the lab and actually test some of these out and see what we mean by kind of what this kind of looks like in the lab, and by mixing a couple little mini double displacement reactions for us. So you should be able to get into the lab or watch the lab video if you were absent on that day.